All right, we're going to pick up with where we left off, and that was discussing the star cycles, the life cycle of the star. And we're going to be talking about once a star forms. Now, once fusion can occur, a protostar is what is given the name of the star. So, a protostar is obviously the first stage, the first development of the star. Once fusion begins to occur, two things are going to happen. The first one is not so great for the star because it's not massive enough, and it doesn't make it to a full-fledged star. It becomes what is called a brown dwarf, and a brown dwarf is not classified as a star. It wasn't big enough. It's a bit larger than your average gas giant planet, but it's too small to form a star, and it fades off into the island of misfit stars. Now, the second option is where our sun and many other stars are currently. About 90% of stars right now were big enough, had enough mass, developed enough fusion to become a main sequence star. And a main sequence star, the main idea behind that is there's enough hydrogen that is being fused into helium, which maintains stellar equilibrium or balance. Once a star is developed, it's a main sequence star. It's got a couple different ways to go, and it's all about mass. It can become the size of our star. It can become what is known as a huge star, which is about 3 times the mass of our sun, or over that, it's a giant star, and there are a lot of giant stars out there in the universe. Keeping in mind that fusion occurs as we'll start with 4 protons, 4 hydrogens, which are nothing else but a proton, and we'll end up with 1 helium. And along the way, a lot of energy will be released. A star the size of our sun, for example, has about 10 billion years of fuel or hydrogen. Once that runs out, it'll start to heat up, expand out, try and fuse helium, and it'll become what is a red giant star. After the helium runs out, it's pretty much done. It expands outward, pushing out a lot of the lighter gases into the surrounding cosmos, and it becomes a white dwarf with what is left. Remember, stars that are bigger need more energy to balance the gravity, so they're going to use up their hydrogen at a much faster rate than our sun because it's smaller. We know that a red giant is a massive star. It goes through the same stages, but because it had a lot more mass, it becomes a red giant or red supergiant. It can go through a supernova, and it can become a neutron star, or if it's big enough, maybe even a black hole. A red giant star or a red supergiant, the key here is fusing some helium into carbon and other atoms, other new elements. Here's our sun compared to a red giant star. And here is our sun down here, if you can see this way down here, to a red supergiant star. A Betelgeuse, there's our friend Betelgeuse, and Antares. A neutron star is about 1.5 mass of our sun. It's only about 20 kilometers wide. Well, folks, that's only about 13 miles wide, but it's very dense. And a black hole is by far the most extreme density. It actually draws the matter in even light. Now, this says it pulls matter in. That's an argument for another day. If we understand Einstein's gravity, we realize that it's probably not getting pulled in, but space is directing it in. But we can see black holes. We can see what they do. We can't see them, obviously, but we can see what they do because they are actually pulling nearby matter into them from a star. So it's stripping away some of the outer layers of a star and pulling it in. We can watch that go. So we know something's going on. Can't see the black hole, but we can see what it's doing. All right, that wraps it up. Hope you understood that. If not, let me know. Have a great day, and I will see you soon.